Previously in Young's double slit experiment, we learned that we have two slits and we have two circular waves being transmitted out from the two slits over here, and they can form an alternating bright and dark fringes on the screen that you place someplace away from the two slits. So this is the experiment that we have done in the Young's double slit section. But now we are going to modify our setup a little bit. Okay. Last time, we used to assume that the slit to be narrow in comparison to the wavelength. So if the wavelength is about this much, the distance between two wavefront is a wavelength. If last time the distance is this much, we usually assume the slit to be narrower or near the same length as the wavelength. So it's about the same size. The wavelength and the slit is about the same size. So at that kind of situation, we call those kind of slits to be narrow. So those are narrow slits that we're talking about when we talk about double slits. The slits are very, very narrow, near the size of the wavelength of the wave, sometimes a bit larger or a bit smaller, but somewhere around there. Okay, so because of that, the wave transmitted through both slits spread out uniformly in all directions to the right of the slit. Okay, because the slit is very narrow, you can assume that the wavefront that managed to pass through the slit is only a very small part of the wavefront. Okay, only a small part of the wavefront can be transmitted through the slit. And we learned before from Huygens' principle that if it's a very, very small part of the wavefront, there's only a few, or maybe you can just assume there's only one source of secondary Huygens wavelets. So there's only one source of secondary Huygens wavelets. You can assume the next wavefront will be a circular wavefront. Then based on Huygens' principle, the wavefronts afterwards will be a circular wavefront. So that's the idea of why if you have narrow slits, your wave transmitted will spread out uniformly. Because based on Huygens' principle, if it's a very narrow slit, you can assume it to be having just one single source of secondary Huygens wavelets. So if there's only one source, you emit it will spread out uniformly, so it form a circular wave. Okay, the same goes for the lower source as well. Both of these will emit circular wave because they are very narrow. Okay, from the perspective of Huygens' principle, this is similar to us assuming that there's only one point on the wavefront, just like what I mentioned earlier. For each slit, that can be considered as source of secondary wavelets. One source only for this slit, one source only for this slit. So if you draw using your compasses to draw the next wavefront, it will be a circular wavefront. Okay, so this is what we did when we talk about Young's double slit experiment. So the slit, now you know that the slit for the Young's double slit experiment have to be very, very narrow, near the same size as the wavelength, around that same region of length for the width of the slits. Okay, but now we are going to move on to diffraction by a single slit. So how does diffraction by a single slit differs from the double slit experiment? Well, we should treat the slits to be having finite width. So just now the slit was so narrow, it is near the wavelength size. But now we need to consider the slit to have finite width. So not so narrow anymore. There's a certain width to the slit over here, or you can think the hole has a measurable size. Okay, the hole here has a measurable size. So let's modify the diagram a little bit. Our width should be something that we can make measurements. We can know the size of the width. Last time it was very, very narrow that we can ignore the size of the hole, but now we are going to assume that the hole is not so narrow anymore, so it's a hole that we can measure its width, and its width, we call it the width of the slit. Okay, so now because this is a single slit, there's only one slit only, we don't need to label it by S1, just call it as S will do. So from the perspective of Huygens' principle, now each element of area of the slit opening can be considered as a source of secondary wave. You know that there will be wave coming from the left, the wavefront will be coming from the left, moving towards the right. Maybe I can sketch it. There's wave coming in this direction. Okay, so when the wave reaches this point over here, only a small portion of the wavefront can pass through, like I mentioned earlier. Only this much of the wavefront can pass through. Okay, so we can assume each element of area of a slit opening. So this is one element, two elements, third element, fourth element, fifth element, sixth element, seventh element, 8 elements. So every element of this area over here, the area of the slit opening, can be considered as a source of secondary wave. And this is why I say it's a continuous distribution of Huygens wavelets, because now each point on the wavefront over here will be considered to be a source of secondary wavelets. Okay, so this is what we learned from Huygens principle. Every dot over here, we can think of it as a source. So now secondary wavelets will be spread out from each source of the secondary wave. So there will be circular wave coming out from the first area. The second area, there will be circular wave as well. The third area, there will be circular wave as well. The fourth area, there will be circular wave as well, so on and so forth. So you see a pattern that looks something like this. You have red, orange, yellow, green, blue, red. Yeah, basically each point over here, there will be circular wave emitting out from it. Each point I label in different color wave. The red one represents the first dot, orange one the second dot, yellow one the third dot, the green one the fourth dot, the blue one the fifth dot. So each element here will be emitting its own secondary wavelets, and all these secondary wavelets over here will overlap in the same region. Okay, so now what happened is it's overlapping of many secondary wavelets, right? So this results in the interference, because interference basically means overlap, but this is overlapping of many light waves, not just two, it's many. So we are going to call it as diffraction. So this phenomena involve a finite wave, a slit of finite wave. We send light over, then the light, because a portion of the wavefront can pass through the slit, every element on the wavefront will be considered as a source. So there will be many sources, many secondary wavelets, all of them overlap in the same region. So this is interference of many light waves. So we call it as diffraction. So right now, what happened in this region here, it's diffraction. It's not many color. This is not red color, red light, orange light, yellow light, blue light, green light. No, they're not different color light. I'm just representing there will be light wave emitting from many sources across the width of the slit over here. Okay, so they overlap each other, causing this diffraction. So we are going to study the pattern produced by this slit wave, by this slit over here. Okay, so if you place a screen over here, the kind of pattern that you will be observing is something like this. Okay, this is the pattern that you'll be observing on a screen if there's a single slit with a finite width. But in the next video, I'll be talking about how are we going to analyze where do we find the dark fringe, where do we find the minima, and where do we find the bright fringes. Okay, so that will leave it to the next video.